Hi there. This is the continuation of section 4.3 in the book. Let's get started. We'll begin with a little bit of review. If A is a square matrix, and we modify A by subtracting lambda from the diagonal values, and then take the determinant, the roots of this determinant, the values that give me a 0 for the determinant, are the eigenvalues of A. For example, if I want to find the eigenvalues for this matrix here, I need to calculate the determinant of the matrix where I subtract lambda from the two diagonal values, but not the other values, set that determinant equal to 0. The determinant is 6 minus lambda times 1 minus lambda minus the product of these terms is a negative 6. And if we FOIL this out, we get lambda squared minus 7 lambda. Negative lambda and negative 6 lambda is negative 7 lambda plus 6 equals 0. One of the plus 6's comes from these two terms, and the other plus 6 comes from minus a negative 6. And so we get lambda squared minus 7 lambda plus 12 is equal to 0. That factors into lambda minus 3 times lambda minus 4. And so our eigenvalues are lambda equals 3 and lambda equals 4. We'll work with this matrix again in a few minutes, so let's save this information for later. This expression that we found, lambda squared minus 7 lambda plus 12, is called the characteristic polynomial of A. If we want to find the eigenvectors for A, we need to examine what happens for each of the two eigenvalues. One with lambda equals 3, one with lambda equals 4. Sorry about that. What we're going to do is we're going to plug each eigenvalue into this system here. 6 minus lambda, negative 1, 6, 1 minus lambda, augment it with all zeros. This is a homogeneous system of equations. And then we're going to solve. And our non-zero solutions are our eigenvectors. So let's try this. If we plug in 3, 6 minus 3 is 3, and 1 minus 3 is negative 2. This is not hard to row reduce. It'll take us 2 steps. I will take row 2 minus 2 row 1, and that gives me 0, 0, 0. And then I'll take row 1, divide it by 3. I'll get 1, negative 1/3, 0, 0, 0, 0. I have one leading entry, and so that means the second column is free in our system. We have a column that represents a free variable. Let's call that free variable t. Then our first variable is equal to 1/3 t, and our second variable is equal to t. And so our solution set is t times the vector 1/3, 1. And this vector is an eigenvector. So one of the eigenvectors corresponding to lambda equals 3 is 1/3, 1. We'll do the same process now for lambda equals 4. We'll start with the system. 6 minus 4 is 2. 1 minus 4 is -3. And again, we can reduce this in 2 steps. Row 2 minus 3 row 1 gives me 2, -1, 0, and 0, 0, 0. And then row 1 divided by 2 gives me 1, -1/2, 0, 0, 0, 0. Again, this column represents a free variable, which we'll call t again. And my solution will be x1 is equal to 1/2 t, x2 is equal to t, and so t times 1/2, 1 is the solution to this system. And so my eigenvector corresponding to lambda equals 4 is 1/2, 1. So let's keep going. We know that lambda is equal to 3 is an eigenvalue, and its eigenvector is 1/3, 1. We know that lambda equals 4 is an eigenvalue, and its eigenvector is 1/2, 1. And that's the eigenvector we're looking at here. This is the eigenvector corresponding to lambda equals 4. And the definition of an eigenvector is that when we multiply the matrix times the eigenvector, we get exactly the same result as if we just multiplied the scalar times the eigenvector. But we're multiplying this matrix 3 times. This is A times A times A times the eigenvector. Here we can replace A with lambda. But I could bring the 4 out to the front because 4 is just a constant. And then once again, I can replace the A with a constant. But constants I can bring out to the front. And so now I have 16 times AV. But once again, when I have A times V, I can replace A with the eigenvector, eigenvalue. So A cubed times 1/2, 1 is just the same thing as 4 cubed times 1/2, 1. And 4 cubed is 64. 64 times 1/2 is 32. 4 cubed times 1 is 64. And we were able to calculate this without ever actually having to raise A to the 3rd power. Let's try a harder example. Let's compute this power here, this matrix, to the 10th power times 5, 1. We would like to know what the eigenvalues and the eigenvectors for this matrix are. So we find the eigenvalues. And those eigenvalues we find by taking the determinant of negative lambda 1 to 1 minus lambda, setting that determinant equal to 0. When we multiply this out, this is lambda squared minus lambda minus 2 equals to 0. And that factors into lambda plus 1, lambda minus 2. And so my eigenvalues are -1 and +2. That's what we're doing first. Then we find the eigenvectors. And this is a process we have to do twice. We have to do the eigenvector corresponding with lambda equals -1. So I'm going to plug in -1 for lambda here. -1 is 1. 1 minus -1 is 2. And I'll skip the row reduction steps here, but the eigenvector that we get for -1 is the vector -1, +1. Then we have to do the same thing again for lambda equals 2. Plug in 2 for lambda, -2, 1, 2, 1 minus lambda. 1 minus 2 is -1. That row reduces to 1, -1/2, 0, 0, 0, 0. And so we get 1/2, 1 as our eigenvector for lambda equals 2. So we have our two eigenvectors. This is neither of the two eigenvectors. But it is a combination of those two eigenvectors. We can find that combination by solving this system. -1, 1, 1/2, 1 gives me 5, 1. Multiply the top row by -1. Gives me 1, -1, half, -5, 1, 1, 1. Take the bottom row and subtract the top row. 1, -1, half, -5, 0, 1 minus 1/2 is 3 halves. 1 minus -5 is 6. Take 2/3 times row 2. And we get 0, 1, 4. 1, -1/2, -5. And then finally add 1/2 row 2 to row 1. And we get 1, 0, -3, 0, 1, and 4. And so we get this linear combination that 5, 1 is equal to -3 times -1, 1 plus +4 times 1/2, 1. Take a moment to double check that that combination works. And what I'm going to do is I'm going to take this matrix to the 10th power and multiply it through by both of these terms. A to the 10th power times 5, 1 is equal to -3 a to the 10th power times -1, 1 plus 4 times a to the 10th power times 1/2 1. And this is the same thing as -3. The eigenvalue that it corresponds to -1, 1 is -1. But the eigenvalue that corresponds to 1/2 1 was lambda equals 2. This is a little strange. We're replacing a with a -1 in this term, but we're replacing a with a 2 in this term, because each of these vectors have different eigenvalues associated with them. All right, we can multiply this out. -1 to the 10th power is just 1, and so we get -3 times -1 is 3, and -3 times 1 is -3. 2 raised to the 10th power, big number, is 1024 times 4 is 4096. 4096 times 1/2 is 2048. And 4096 times 1 is 4096. And then when we add these together, 3 plus 2048 is 2051. And -3 times 4096 is 4093. And we have done a lot of calculations here. We've done a whole screen full of calculations, but we never once had to actually multiply this matrix out 10 times. We never had to do anything that tedious anywhere on this page. And that's important. What we did in the last example was we used eigenvalues and eigenvectors to replace having to calculate this matrix to the 10th power with just calculating the scalar, lambda to the 10th power. I did have to calculate -1 to the 10th and 2 to the 10th, but I never had to calculate this matrix to the 10th power. And this gives us a good way of answering questions about the long-term behavior systems that involve the repeated application of a linear transformation. Let's try this example. Let A be this matrix here, 1, 0, 3/2, 1/2. The eigenvalues are 1 and 1/2, and the corresponding eigenvectors are 1/3 and 0, 1. I would like to calculate a to the t power of 2 times 2, 2, as t goes to infinity. Well, again, 2, 2 is not one of these two eigenvectors. 2, 2 is not an eigenvector. But it is a combination of eigenvectors. Or if you want to say a linear combination of eigenvectors. Specifically, 2, 2 is equal to 2 times the first eigenvector, 1, 3, plus -5, -4 times eigenvector 0, 1. And so the limit as t goes to infinity of at times 2, 2 is the same as the limit as t goes to infinity of at times 2 to the 1/3, 2 to the 1/3, listen to me, sorry, 2 times the vector 1, 3, plus -4 times the vector 0, 1. When I distribute the a to the t, I get 2a to the t times the vector 1, 3, minus 4a to the t times the vector 0, 1. At this stage, I'm going to replace A with the eigenvectors. So the eigenvector that corresponds with 1, 3 is 1. So 1 to the t times 1, 3. And the eigenvector that corresponds with 0, 1 is 1/2. But as t goes to infinity, 1 to the t is just 1. But 1/2 to the t goes to 0. And so this limit is 2, 6. On the next page, we're going to go through the same example. We're going to just go through it a little more slowly and walk through all of the steps. The first thing we did was we rewrote the vector 2, 2, which was not an eigenvector, but we wrote it as a linear combination of the two eigenvectors. 2 times 1, 3, and -4 times 0, 1. And then we're going to substitute this linear combination into this limit expression. We substitute this linear combination to a limit we want to find. Instead of calculating a to the t times 2, 2, we'll be calculating a to the t times this linear combination. In the next step, we're going to distribute the a to the t inside this linear combination. And so we get 2a to the t times 1, 3, and 4a to the t times 0, 1. The next step, we're going to replace a in each term with the eigenvalue that corresponds with each eigenvector. So the first time a gets replaced with a 1, but the second time a gets replaced with a 1/2. And this is what enables us to take this limit. 1 to the t is just 1, so this is 2 times 1, 3, which is 2, 6. And 1/2 to the t goes to 0, and so anything times 0 doesn't change the answer. Let's do one more example. Here's my matrix A. The eigenvalues are 0.2 and 0.5, and my eigenvectors are 2, 3, and 2, 1. What I would like to do is I would like to find this limit here, a to the t times 6, 5. Okay? So I need to find a combination of these two vectors that adds up to 6, 5. And that combination so we want to find a linear combination of eigenvectors that adds up to 6, 5. And that combination is 1 times 2, 3 plus 2 times 2, 1 equals 6, 5. We'll substitute that combination into the limit. So what we would like to find the limit as t approaches infinity of a raised to the t power times the combination 2, 3 plus 2 times 2, 1. Distribute a to the t. This gives us the limit as t approaches infinity of a to the t times 2, 3 plus 2a to the t power times 2, 1. And now we will replace a to the t with the eigenvalues. The eigenvalue that went with 2, 3 is 0.2. And the eigenvalue that went with 2, 1 was 0.5. But we can solve this. 0.2 to the t as t approaches infinity is 0. And 0.5 to the t as t approaches infinity is also 0. And so what is this limit? This limit turns out to be the 0 vector. After you do a few examples, this gets a little bit better, but the first step requires that we are able to find a linear combination of these eigenvectors that adds up to 6, 5. And whether we can find a linear combination has to do with whether these two vectors forms a spanning set for R2, which would make it possible to find this linear combination in all cases. And so we might want to know if these two vectors are linearly independent or not. And theorem 4.20 in the book is a theorem that helps us test for linear independence. The theorem says that if we have an n by n matrix and we have distinct eigenvalues of A, then the eigenvectors that correspond with the distinct eigenvalues, distinct in this case means that no eigenvalue is a multiple root. Of the characteristic polynomial. Or no value is repeated in the list. Then distinct eigenvalues always give linearly independent eigenvectors. The book gives us a complete proof of this theorem. I'm going to just prove this in a special case for 2 by 2 matrices. This abbreviated proof has simpler notation. It's not as cumbersome as the full proof, but it shows the important idea that multiplying by the matrix A, we can replace the A with the eigenvalues in the equation. So let's look at the abbreviated proof just for n equals 2. We have a 2 by 2 matrix with eigenvalues that are distinct. They're not equal to each other and corresponding eigenvectors. Our goal is to prove that they are linearly independent. So let's say we have a linear combination that adds up to 0. In order to prove that these two vectors are a linear combination, we need to know that that linear combination is trivial, that C1 and C2 have to be 0. This is our goal. We want to show this. And so what I'm going to do first is take this linear combination and multiply both sides by lambda equals 1. Lambda equals 1. Lambda sub 1. C1 times lambda 1 times V1 equals C2 times lambda 1 times V2. But I'm also going to multiply both sides of this linear combination by the matrix A. C1A V1 plus C2A V2 equals 0. And this gives me two different equations. One where I multiplied by a scalar and one where I multiplied by a matrix. And so now we have C1 lambda V1 plus C2 lambda 1 V2 equals 0, and C1 AV1 plus C2 AV2 equals 0. But by definition, an eigenvector satisfies AV equals lambda V for its eigenvalue, And so I can replace the A in AV1 with lambda 1 and replace the A in AV2 with lambda 2. And so I have these two equations where the first term is identical, but the second term is different. I'm going to take these two equations and subtract them. When I subtract them, I get C2 times lambda 1 minus lambda 2v is equal to 0. Now, v is not the zero vector because an eigenvector must be non-zero. This can't be 0 because eigenvectors are never allowed to be 0. This term can't be 0 because we said up here that these eigenvalues are distinct. And if they're different from each other, their difference cannot be 0. And therefore, the only way that this product can equal 0 is if C2 is equal to 0. So it must be the case that C2 is equal to 0. Now, if I go back and repeat this same argument, but right here, instead of multiplying by lambda 1, I multiply by lambda 2 instead, so that both of these terms were lambda 2. Then when I got to this pair of equations, it would be the second term that matches and not the first term. And so I could do the subtraction process again and show that C1 is equal to 0. In other words, if we repeat the same argument but multiply by lambda 2 in the first step instead, we get this equation. V can't be 0. Lambda 2 minus lambda 1 can't be 0, and therefore C1 has to be 0. And that's why V1 and V2 are linearly independent. Thanks for watching.